and then let me share my screen. Okay, recording started. Good morning again. Let me share my screen now. Okay, so here it is. Perfect. And now let's go here. You should see now on your shared screen my website, tutorials of climate change adaptation. If you don't see it, let me know, please, because with this version of Linux, I don't see, just 1 second, I make a check. Yeah, I think you see it. I don't see the red rectangle around the screen that you shared. Okay, good. So just to make a brief recap, as I said, we went through the introduction, the premise. I have to change the order of these links in order to, to match the order we discussed them, okay? And then we talked about the Earth system, and as I said, sustainability is something for you to read. And then we went to discuss the risk-based adaptation design last Monday. And then last Monday, in the second part, we talked about the climate change problem. Okay, what I want to do today is to move forward with the discussion of the climate change problem. We still have some minutes, some slides to discuss. And then, as I mentioned to you, I would like to go back to the risk-based adaptation design with some example of application. This is what I want to do today in these couple of hours. Okay, good. Let's go to the climate change problem. Climate change problem, we discussed it through a PowerPoint, as you may remember, which is this one that you can see on the screen. Let me go to presentation mode. And we talked already about these slides. And I just want to, I think we can start from here today. So this is just a brief slide to recap that climate change is not a new problem, and it's a problem that started to concern the human community about already in the 19th century, actually, when we experienced the impact of the Industrial Revolution. We realized that, as I probably already mentioned to you, air pollution was a problem at that time. Air pollution was a big problem with some severe impacts on human health. And the air pollution was so intense that people could really perceive, especially in the industrial areas, of course, the impact of the dust, and they could perceive that this was extremely not only dangerous for the earth, but also dangerous for the environment, because they could see really an effect of darkening also of the air, especially during the works, the industrial works. And at that time, in the 19th century, also scientists, observers, started to perceive that the climate was changing. They realized that the glaciers were retreating. Just to give you an idea, in this part of the Apennines, in the Emilia-Romagna region, it seems that in around 1750, so earlier than the 19th century, there still were some permanent glaciers, some permanent snowed areas covered by snow. And then when the little ice age terminated, these remains of snow during the summer, these remains of permanent snow disappeared. So already in the 19th century, people could perceive that the climate was changing, and therefore they also got aware of the air pollution, and they first hypothesized, some scientists, the possible impact of a kind of greenhouse effect. So the greenhouse effect was first identified in the 19th century. And then in the following decades, the situation in terms of environmental impact became, especially in some countries, especially in the Western countries, became more concerning with rivers that started to become polluted, etc. And also the attention on the necessity to preserve the environment and to make sure that the environment could survive for the future generation, this concern became formalized. We already said that around 1960, the humans realized that water was to be protected. It was not an infinite value. And around that time, it was clearer and clearer that the carbon dioxide was causing some effects on the dynamics of temperature. And you just have to keep in mind that the situation was not so clear as now, because between 1960 and 1980, there was an episode of global cooling. If you look at the progress of global temperature, you have the graphs. We showed the graphs before. If you look at these graphs, you can see that from about 1960 up to 1980, the global temperature decreased, and this, of course, was a little bit puzzling for people to understand, because on the one hand they realized that there was a warming going on the other hand they if they looked at data they could see that there was something that was not matching what they were expecting. Global cooling was later attributed to orbital changes, temporary orbital changes, and increasing human emissions of aerosols, because aerosols may have this effect of screening in a way the sun rays and therefore reducing the emission of energy from the sun. Anyway, after 1980, the process, probably due to also to natural variability, terminated. And then, as you know, from the end of the 80s of the past century, the temperature started to increase. And therefore, now we are fully aware of the problem, fully aware of the concern, even if, as I said, there are still many unknowns, and this is why we are studying here climate change. Okay, let's skip this, because I think we already talked about the fact that global warming is a controversy, and global warming presents several unknowns. I just would like to emphasize once again, because I already emphasized it, the need for an interdisciplinary approach. And given that we are at an engineering school here with students who are not studying engineering, but in an interdisciplinary context, I want to emphasize the role of engineering. And I want to emphasize it because recently we experienced at the global level a kind of distrust in engineering. Distrust means that, environmental impacts may be attributed to engineering because infrastructures, changes of the landscape, they of course need a design to be made. We need also to design a technical strategy, and this is the contribution that is specific for engineering. And therefore, engineering on the one hand may be seen as a responsible discipline of the discipline that took the fault of materializing the human impact on the environment. And as I said, on the one hand, we can attribute some faults to engineering in this sense, and the natural reaction was to claim, to call for a back return to a natural environment. So the call that the Green parties, who gave a very significant contribution in order to raise the attention on the concern, but their call was essentially aimed to go back to a pristine condition. And of course, on the other end. So on the one hand, they attributed the fault to engineering, and on the other hand, they called for a way back to the pristine conditions. Actually, this is a call that it's not very useful for sustainable development, because actually, as you know, the relationship between human and nature is difficult, and for humans it's extremely difficult to survive in a fully natural condition. And in fact, during the history, humans improved their interaction with the natural condition. They devised heating plants, cooling plants. They devised measures for protecting themselves from natural hazards. So actually, we can't forget that our interaction with nature needs a mediation. And this mediation needs an interdisciplinary contribution. So if we want to really get to a sustainable future cannot be a future where humans, in a way, give up to their effort to adapt to an environment that is naturally difficult. A sustainable future requires such mediation, which I mentioned, which necessarily has to be interdisciplinary. So we cannot discard the role of economics, we cannot discard the role of natural sciences, we cannot discard the role of politics, and we cannot discard the role of engineering. Actually, the distrust in engineering has implied a kind of lowering of the impact and the influence of engineering. And the purpose of this course, of this interdisciplinary audience that I am promoting, is also to reinforce this cooperation. There is a box on my website called Engineering Science, which explains what is the role of engineering and why this dialogue is important, which is also discussed here. So let's skip this because it's something that I already mentioned. I just want to emphasize, you see the last but one link, black swans. Black swans, look on Wikipedia, on Google, what is the meaning of this concept that has been introduced in order to characterize the occurrence of events which we think they are impossible, but sometimes they happen. And this will be the subject of a specific part of a lecture. So the impossible event, the event which we think it's impossible, but at the end of the story, it may happen. But I don't want to anticipate this discussion because it's very nice. It's a big problem. And I just want to dedicate the required attention later on. Okay, tipping points, we already discussed them, so let me skip it. Societal tipping points, let me skip them. And I want to dedicate some minutes to discuss about the data, because we already mentioned that we need information, we need data in order to characterize climate. We already mentioned that unfortunately we don't have an extended database for reasons that are not completely known. And we already emphasized that this is a problem indeed. It's a problem because actually our unknowns regarding climate, regarding the environment, require research, but an essential support for research is experiments. And experiments means data. Our data represent our experiments. When you go out and measure the temperature in a location, you're making an experiment. And this experiment, for instance, is finalized to understand the natural variability, the fluctuations. So these data for us represent experiment. Data are not only scarce, in some cases they are also not accessible. Not accessible because taking data requires money, requires resources, and therefore who is paying for that tends to claim the right to use the data, to sell the data, which is understandable. It's perfectly understandable. And on the other hand, you get the problem The problem is that if we cannot share the data, if we cannot use the data, if we can have the data only if we pay for them, there is a big problem. The big problem is, first of all, equality of opportunities. So if research can be done only by the scientists who have financial resources, this is a big limitation for research. It's a big inequality. It triggers, it's an obstacle, it's a barrier to sustainable development. It's a barrier to inclusivity, and we are getting the meaning in these years of what inclusivity means. Just 1 second, because I see that there is something which in Teams that is alerting me. No, I think it's no problem. Okay, thanks a lot. Sorry for that. So, I mean, you understand why there is a push today towards open data, open science. You know that I am passionate of it, and the reason why I'm passionate of it is that I experienced the problem. And I could see the big development that we had when we could exchange climate data with Austria, with Germany. I mean, we are sharing the Alps. The Alps are a hotspot for climate change. So it was, to me, something really not understandable that we couldn't share data taken on the two sides of the Alps. And I was really excited when finally I could have access to it. And this was an initiative that was taken by the colleagues Austrian colleagues who, regarding water cycle, you know that I'm studying water cycle in particular, regarding water cycle, they made an effort, and also they dedicated some funding to creating a bank of open data. But on the other hand, even if we shared all the data available, there are some gaps that we need to fill, and the gap is in the past. Today, keep into account that we are collecting a massive amount of data regarding environment and regarding the Earth system in general, including the societal component. Thanks to remote sensing, thanks to satellite missions, which are increasing again and again, we are now collecting a huge amount of information. And through mathematical models, through digital twins, so through digital replicas of the Earth system, we are generating again an impressive amount of petabytes every day. So data that, I mean, it's really unprecedented, and such that several of these data are still not used. Now it's a key research question. How can we effectively use this massive amount of Earth observation? On the other hand, if you look at the time span covered by this massive amount of data, is the past 10 years, 10, 15, maybe 20. For some satellites is 20 years. So there is a gap in the past. There is a gap in the past. You know, I think I already mentioned that rainfall observations started in Italy. It was the first country in the world to start with rainfall observations at daily time scale. And they started in 1725, 1713, sorry, with the rainfall series in Padua. You can see on the slide it is mentioned. So how can we go back in the past more? And you may have heard that there are indeed researches that are finalized. I'm sorry, before I raise the question, look at this series, which is really a treasure. This is, sorry for the Italian captions, it's the rainfall series in Bologna. And the annual rainfall. Actually, the series is collected at daily time scale, and I'm plotting here only the annual rainfall because it gives an idea of the natural fluctuations. It's indeed a great treasure because it delivers more than 200 years already of information on local rainfall. And it is something that is extremely important to check the reliability of our models, etc. Now, as I said, how can we go back in the past? You may have heard about proxy data like tree rings, like I-scores. These data are extremely important because they give us indeed not through observation, but through proxy of these observations, they give us information on the past climate. So if you look at tree rings and we have the opportunity of doing that because we cannot cut trees on purpose, of course. If you look at tree rings, you can get information on the climate behavior at, on the other hand, annual time scale. You don't get daily information, you don't get monthly information from tree rings. You get information at annual time scale. And I would say that you understand that we say annual time scale because three rings, each three ring represent a year. On the other hand, you understand that the growing season is not extended over the whole year. So we say annual, but actually it's not really annual. It refers to the growing season each year. Another opportunity is given by I-scores. I-scores keep witnesses of past concentration of isotopes in the atmosphere. And we know from other researches what was the concentration of isotope in the atmosphere in the past, and therefore we can date these layers of ice. And of course, if you see that a layer is thicker, it means that during that year, during that period, they got a more significant contribution in terms of ice growing. And therefore, with the ice cores, we can reconstruct basically the past climate, and you see that we can use several different isotopes. They give different reconstructions, but the general behavior is more or less similar. These proxy data therefore have a couple of, let's say, several limitations, but what is more significant is the time resolution, which is in the best case annual. And also another limitation is, of course, uncertainty, because the relationship between the proxy and the climate variables is subjected to uncertainty. And therefore, when we look at tree rings, it is usual practice not to use only one tree, but to use several trees. Fortunately, nowadays, there is the opportunity to have access to open banks of tree ring data. They are not homogeneously spread. So, for instance, for Italy, we have only a few of them. But it is a good opportunity to be able to get information from several sources, several trees. And this information can be matched with the information delivered by other proxies. And of course, merging all the available information, as I already pointed out, allows us to minimize uncertainty. Now I have a PhD student that is working on reconstructing the river flow of the Po River in the past by using tree rings. Our observation for the Po River go back to the beginning of the 19th century. We don't have any observation of water level or river flow before the beginning of the 19th century. But for the purpose of getting information on past floods and droughts, we would like to try to extend in the past the reconstruction of the time series of the river flow for the Po River by looking at tree rings. So now the student is studying the correlation between the river flow that we have actually observed with the tree rings in the same period. So he's studying the correlation between the river flow observed in the 19th and in the 20th century with the tree ring data for the same centuries, for the same period, in order to find the combination of trees that gives us the best correlation. And then the same tree can give past information, which allows us to reconstruct the series into the past. It is not easy because the correlation is not so significant. You know, we are looking at correlation between river flows and the tree rings. So, and tree rings that are not really located in the Po River basin. So, I mean, it's a fascinating research, but the uncertainty is significant. But I want to emphasize the concept. There is a lot of research on this proxy data. Okay, now I'm here. We are talking about models, and we are talking about models, but I prefer to skip this slide for now. Here we are talking about models and their uncertainty, but there will be a lecture dedicated to climate models, and we will have the opportunity to discuss uncertainty in that lecture. Okay, now let me close with this slide. This slide gives to you, in order to give a final information on the climate change problem, gives to you data that are derived from Munich RE. What is Munich RE? It's a database that is open. You see the link in the upper graph. It's open, so the link can be directly clicked on my website, not from the PowerPoint, of course, but on the website you can click on it. And it's an open database of what? Of damages. Damages given by natural hazards in the starting from, you see the graphs here, starting from about 50 years ago. So we can get the progress at the global level or regional level, because you can select also regions. We can get the progress of the damages for we experienced for natural hazards. And they are collected, this data, by an insurance for insurance company. And I want to better explain. The insurance companies which insure, for instance, people against natural hazards. So you can get your home, your house insured against the risk of an earthquake. The insurance company which insure for damages that can be very significant, they are obliged to get in turn insured in order to avoid that the insurance company may experience a default. So in order to protect the final beneficiary of the insurance, which is us, the insurance company which insure us are obliged to get insured. And the insurance for insurance company is particularly interested in the events that can cause the failure of an insurance company for the end users. So they are very interested in the black swans, in the events that are very rare and cause a big impact, precisely because they are very rare. So they have this data, and you can see the progress of losses at the global level from weather disasters. And you see in the upper graph that the progress is trendy. It is trendy, meaning that there is a trend, there is a clear trend. If you look at the bottom graph, these are losses divided by, or let's say losses as percentage of the global gross domestic product. So they are losses divided by the global gross domestic product. And what this graph tells you is that it's less trendy. So it means that the damage caused by natural hazard, for sure it is caused by climate change, but on the other hand, it's also determined by the exposure. The GDP, gross domestic product, means exposure, because a country that has a high GDP becomes more exposed. A land that has a high GDP becomes an investor on the same land, and it's more exposed. So these two graphs, I think, are very significant, are very interesting, because they clarify the complexity of the problem. The complexity of the problem. Okay, good. I think this is the last one. Yes. So let's go out from the PowerPoint and let me go back to the website. And now it's time, before we make the break, to go back to probability, or let's say go back to risk, and in particular to probability, because we stopped here. I just want to show you. So if we open the video last time, which is this one, we stopped, should be already, okay, it's already, just 1 second, I stop it. It's already at the point where we stopped with the discussion of the drivers of risk, and in particular, we concluded with the discussion on probability. And what we said is that, if you look on the right, we discussed the frequentist estimation. We also discussed the Bayesian estimation, but we stopped with the discussion of the frequentist estimation, which is given the estimate of the probability of an event H, in this case H because it was heads, it is an experiment of tossing a coin. So this probability of getting an head is given by the number of heads divided by the number of tosses, so the number of outcomes, the total number of outcomes. And we said we expect that this number is about 0.5. And then we said that this is a good way of estimating probability of an event. And then I said, let's stop here because the discussion on probability is not finished. But as I said I want to make an example with the practical exercise. Okay, let's go out from this video, and let me just tell you that as I promised to you, there is now an additional link, risk-based adaptation design. It's the lecture that I'm writing on the web, just a second that it opens, which follows what I told you on Monday. And it's still a draft, you see here, draft, because it's not finished, but it's almost finished, okay? And in this lecture, let's see where we got probability estimation, and in an informal introduction to probability, we got here pH, let's see, here we got to this formula equation 2, pH is equal to the number of heads divided by the total number of tosses, which is called here NTOT, NTOT. Good. This is perfect. Now, let's make an experiment, and a numerical experiment to better get. So don't read starting from here, okay? Wait a moment. And I still don't have the PowerPoint. Let's now get harnessed, get equipped to make an experiment. And there is, if you go down in the web page here, a box, a yellow box. It's the first yellow box in the web page. Let me expand it. Okay, so you see it on the screen, not too much. The R software. Let me make this introduction because I want to make this experiment with a public domain software. I don't want to use a software that is commercial, because I assume that almost all of you know how to use Excel. I say almost because I don't want to give anything for granted. So, but in general, my experience suggests that the students have a good confidence with Excel, which is a spreadsheet and allows you to make computations. But and also my experience tells me that a more limited number of students have a good experience with MATLAB. And some of you have also an experience with R already. R is something that we can call as a clone of MATLAB. It's not a clone, really. There are some clones of MATLAB, public domain clones. We don't discuss them here. But R allows you more or less to make the same things that you can make with MATLAB. And the advantage of this software is not only the fact that it's public domain. The advantage is also that this software allows you to manage a bigger amount of data, of numbers with respect to a spreadsheet. And the reason is that this software is more essential, like MATLAB is. Softwares like MATLAB, like R. There are other examples which I could give. They are more essential, which means they are less user-friendly. The disadvantage is that they are more difficult to be used. On the other hand, the advantage is, as I said, the capability of being able to crunch a big amount of numbers, to digest a big amount of numbers. And this is what we need today, because I mentioned that with Earth observations, we need to get equipped to manage huge amounts of numbers. If you are interested in analyzing climate change, but also in getting information on climate change, you need to get equipped to manage a huge amount of data. So you may have heard about GIS, Geographical Information Systems. They are specifically conceived for visualizing and analyzing Earth observations. R is similar. It's related. You can make analysis of geographical information data also with R. So these softwares, which allow you to get information on climates, it's an essential tool for you if you are interested from any discipline to understand on your own how climate works, how climate is changing. And it is important that you have the opportunity of understanding on your own. So let's install the R software, and then in the next, after the break, we will make some application. Let's install it before the break. So during the break, I hope that you may also, if you experience any problem, which I don't think, but during the break, you have the opportunity to complete the installment. First, I am working on an operating system that is not not Windows, not Mac. So what you see on my screen is a little bit different from what you see on your screen. I am working on Linux. I'm not sure if there are Linux users among you. If you are a Linux user, please write on the chat, I am a Linux user, because it's important for me to know, and I will check with the pool in a moment after the break. I think it is a better thing. Let me start a pool. Don't write on the chat, wait for the pool. Okay, so look at this yellow box. There is written, the R software can be downloaded here. Okay, and let me open it in another tab. So I clicked on here, and you get on this page. Okay, now what you have to do, by following the instructions that are visualized in the yellow box, I go back here, click on CRAN on the left. Okay, let's go back to the website of the ARS project, CRAN on the left. Here you get a list of mirrors. Just choose the first one is fine. Okay, click here, and then you get to this page, and so you have the choice between the 3 operating system: Linux, Mac means Apple, Windows. Let's click on Windows. So the majority of you for sure are using Windows. Let's click here. And then you get this download page where you can select between base, contrib, bold, contrib, bar tools. Okay, click on base. You just need base. And just keep into account that if you are not a Windows user, if you are a Mac user, the page may be a little bit different. If you are a Linux user, for sure it's different. So this is for Windows. Click on Base. And then finally you get to the download link. So you can click here and then the download starts. You can save it on the desktop. Once it is downloaded, double click on it. I can't follow you in this because I cannot double click on it because it's a Windows executable. I am a Linux user. I cannot use Windows programs. But if you double click on it, you have the classic installer of Windows which starts. And at the end of the story, you will get some options. Select always the default. Select the default option, 3-4 clicks, and you get the software installed. Once it is installed in your application menu, you will find a directory which is called R, just with a capital R. You open it and you get the final click to start up R. And you will get a kind of console. What you get is something similar to this. Let me show you. At the end of the story, you get something that is similar to this with some menus in Windows. In the top of the window in Windows, you have some menus like I have here, but your menus will be different. And you get something, a disclaimer, like you can see on my screen. Don't do anything. If you get here, you are ready to start, but we start together. You don't need to do anything. Okay, now I would make a 10 minutes break. Do you have any question? Let me just share the screen and let me see if there are any questions in the chat. Okay, I don't see any questions. So as usual, I'm turning off my camera and mic, and let's meet again in 10 minutes. Thanks.
We can't hear you.
Sorry, we can't hear what you're saying. I think there is a problem with the sound.
Chat. I turned off my headset. Now you should hear me. And I was saying that you see the poll. Please cast your vote. I was saying that I see a Linux user. You are a black swan. So I'm very happy of you. And good. Let's now I shared my screen, and let's now go to screen sharing again. Okay, perfect. Let me just see the pool. Okay, good. So we have 2 Mac users and 1 Linux user. Okay, now open R, please, and you should get to a console, which is similar to what you see on my screen. Okay, the console is an environment that is waiting from your input from the keyboard. You have also some menus on the top if you are a Windows user. Just forget about them for now. If you have any issue, I think you can follow me even if you don't repeat yourself what I'm doing. But if you decided not to follow me by repeating what I'm doing now, that's fine. But if instead you are having an issue with the installation, you can write on the chat, or you can step in with the micro, because your issue may be others' issue. So I'm keen to discuss with you and to solve together the problem if you have an issue. Now, otherwise, let me move forward. And the best way to move forward is to look at my web page. I think it is just 1 second. It is 1 second. Let's look at my web page. It's here. First of all, before I close this window, this is the R website. You see there is a link on manuals. Let's see what's there. The first link under manuals is an introduction to R. This is a very nice guide. It's short, it's very useful. So just want to tell you, if you click on PDF, you see it's here. And you don't need to read it. I mean, you don't need to become an R expert. As I said, this is not for the exam. This is just for selecting a common platform, open source and public domain, to make some exercises together. And I prefer to select this for the reasons that I already mentioned to you. But you are not obliged neither to make the exercises and nor to make the exercises with me, and therefore you don't need to read this. But if for some reason you want to increase your knowledge of this platform, this is the good way of doing it. For following me, you don't need to read this guide. Okay, let's go back to the website, and I am skipping now something on the web page, but because I want to start with the experiment. Okay, so you see that there is a first exercise which you can see on the screen, which reports instructions that in order to make the exercise. To make the exercise, you can just follow me by copying and pasting. So before even commenting, let me explain to you, if you want to follow me, what you have to do. So this is under, between the commas, is the R instruction that you need to copy and paste from here. So let's see here. If I make a selection here, it is important that I select everything is between the commas. I right click, copy. Then I change my window. I go to the R console here. Sorry, it's here. And then I go over the console with the mouse, right click, paste. Let's press return. And you see a number, a result, 2. Okay. Now, let's press arrow up. You have the 4 arrows in the small keyboard with the 4 arrows on your right, on the right of your keyboard. Let's press arrow up, okay? And look what happens. The software gives you back the previous instruction. Let's try to run it again. I press enter. And you have a different result. And then we can understand why later. Again, arrow up, another trial, another outcome. Arrow up, another trial, another outcome. Arrow up, another trial, again and again, okay? Again and again. This is an experiment of a dice rolling done by numerical computation, okay? I think we are still missing a 1. Let me see. Yeah. Okay, we just, okay, I got a 1, okay? Perfect. Now, let me better explain. First, let me clear the screen, okay? And Control L to clear the screen. You have to press Control plus L together, okay? And let me recall the dice, the instruction for the dice rolling. Okay, let's comment on what does this instruction mean for R. And before moving forward, let me just making a short premise. With R, you can make simple computations like 2 plus 2, 4, 2 times 3, 6. You can assign variables like A equal 11. And then you can use the variables to make computations. A times 2. Just 1 second. Okay. So you can assign vectors. So instead of A equal 11, let me write A equal, in order to create a vector, you need to give this instruction. Follow me, C. C is, in the R language, the instruction that to create a vector. And it's a function. So R uses functions, and it uses a function to create a vector, what they call functions. Functions in R are instructions which make a computation depending on arguments. Okay, so C is the function that really doesn't make a computation. It creates a vector. I need to give the arguments. The arguments are the elements of the vector. In R, arguments are to be given to the functions between parentheses, round parentheses. So let me now give the element of the vector. They must be separated by commas, like 1, 2, 3, 4, 5. And then I have to close the parentheses. Now, if I type A, I get the vector. And if I type A times 2, I get each element multiplied by 2. Of course, I introduced several things in one time. And of course, you may have some questions like, how can I know the functions that I can use? How could I know to create a vector if I didn't have any information? Because of course I told you, but what if you didn't have any information? Okay, first you can read the manual, but the nice feature of the public domain software and open source is that you can easily find help on the web. And let me give you an example. Let me start a new tab here. A Google tab, google.com. Okay. And let's search for creating a vector in R. You see that there is already a search in Google, creating a vector in R. Good. You can create a vector in R even without clicking, using C, primitive function. This is exactly what we did. In R programming, the vector contains elements of the same type, and the types can be logical, integer, double, character, complex. Okay, this is already too much, okay? And if we click on it, I'm quite sure that there must be some example. Let's see, 1 second, it's a bit slow. Continue with recommended cookies, just 1 second, it's not continuing, okay. Syntax of C, okay, and here there is an example. Sorry, it's a bit ID. You see that here there is instead of an equal sign here, I'm selecting, okay, selection over break doesn't work. Instead of an equal sign, there is this combination of keys, a minor plus a minus, which is a synonym in R for equal. Just use equal and it's easier. And then you see that there is an example to create a vector. Okay, let's forget about the two following rows. Let's just keep our attention on the first one. What follows is something that we don't need now. Good. Okay, so let me go back to the console. So you see that getting information, getting help with the public domain software, it's easier. And this is indeed interesting. Very good. Now, let's clear the screen and let me go back by clicking arrow up several times to the instruction for rolling the dice. So here you see that I have two nested couples of round parentheses. It means that I used the two functions, okay? And the two functions are floor and runif. Okay, let's start with floor. Floor is easy. If I make floor of 1.2, it gets rounded to the lower integer. Even if I did floor 1.1, I would get 1. If I, for instance, made round 1.2, I'm not sure if it is the correct name for the rounding. Yes, it is rounded to the nearest integer. So round 1.6 gives 2, just to give you an example. But let's focus on floor, okay? Floor rounds to the lower integer. Good. I want an integer from the result of rolling a dice. So this is why I use the floor function. Now, In R, I could also generate integer numbers, random integer numbers. So what I used here, the floor function, which rounds the generation of a real number, it's not the only way. But I wanted to use this way because it allows me to introduce to you two nested functions. Okay. Now, what is then the second function? runif. Okay. And let's use it alone. runif. And then the argument. The argument which I used there are 1, 1, 6.9999. Let's see what is the result of this. It's a real number. Okay, this is not really, you may say it's not really real, because real means infinite digits, but actually it is stored in R as a real number. Okay, let's try to repeat it. Another real number, different. So this function runif generates a real number, only one. Why only one? Because it's the first argument. So let me just write it again. runif. How many numbers? One. This is the first argument, comma. Now it needs to know the range. Okay, so the range which I gave is 1, lower limit of the range, comma, the upper limit of the range. So in order to generate a dice rolling, my idea was I generate one only, a real number in the range 17, because 6.999999 is 7, okay? And then I round to the nearest integer. So everything is comprised between 1 and 1.999999 is goes to 1. Everything is generated between 2 and 2.99999 goes to 2, etc. So if I round it by getting the floor, I get an integer, which is the lower one. Runif, this is important, when I use it, the generation of the real number within the range takes place with the same frequency across the range. So the number of outcomes between 1 and 2, between 1 and 1.9999, is the same number of outcomes between 2 and 3, the same as 3 and 4, like in rolling a dice. So now you understand this function to generate a dice rolling. You see, 3, 1, 2, 6, 5. By chance, all of them are different. Now I have a repetition of 2. Given that in each sub-range between 1 and 2, between 2 and 3, the generation of the real number occurs with the same frequency over the range, over the full range, between 1 and 6, then by rounding the real, I get outcomes from rolling the dice which have the same frequency. Now you may be in doubt. You may say, but is this true? Okay, now let's prove whether this is true. Let's perform a lot of rollings, like 1 million of rollings, not one by one, 1 million of rollings, and let's count the number of 1, the number of 2, the number of 3, over 1 million, in order to get sure, to make sure that indeed the number of 1 is the same as the number of 2, the number of 3, okay? So let's estimate the probability of 1, the probability of 2, the probability of 3, the probability of 4, 5, and 6 through the frequentist approach, okay? Okay, let me clear the screen. And let's go back to the web page to get the instructions. Okay, so this is the second instruction. Rollings, I define a vector. The vector, I don't need the C function here because it's defined through the floor function. So selection, I copy it, I go on the console, and I paste it. Paste. Perfect. I generated 1 million of dice rollings with this function. You see that the argument of RUnif, the first argument, is no more 1, it's 1 million. So it didn't generate just a number, it generated 1 million numbers, and automatically they were put into a vector, of which I computed the floor. So if I want to know the length of rollings, it's 1 million. The length of the vector can be computed with the length function. Now, of course, we cannot look at 1 million of outcomes one by one. I could look at the first 10 just to have an idea, for fun. And if I want to visualize only a part of a vector, I have to type on the console the name of the vector and in square parentheses the range of indexes I want to visualize. These are the first 10. Okay. Now I want, as I said, to compute the number of outcomes which are equal to 1. Let's go back to the web page and let me use the length function. Okay. Let's select this one. I copy it with the right. I go back to the console and I paste it. So before I press return, let's look at this instruction. So there is a length function, okay, which is counting the number of elements of the vector. Which vector? Rollings, but not the whole vector. You see that after rollings, between square parentheses, there is a specification, which means that I am referring only to some indexes of rollings. And what indexes? Those that correspond to rollings equal 1. So this instruction, length, let's forget about the division by 1 million for now. This instruction gives to me the number of ones. And you may have several questions here, like, why two equal signs? This is an R convention. It is an assumption of the language, so don't be bothered by it. I mean, you just have to know that you have to use two equal signs when you want to give a condition to determine which indexes of a vector satisfy that condition, which values of the vector satisfy that condition. Okay. And what about the number of 2? You see, it's very similar, okay? Number of 3, very similar. Number of 4, similar. Number of 5, similar. Number of 6, similar. So it means that my code worked well. I devised a code to simulate the rolling of a dice. Look, when we talk about a mathematical model is precisely doing the same thing. It's emulating with an analytical computation a real world process. It is twinning a real world process. So what we used in this half an hour is a mathematical model, which gives a perfect replicate in terms of outcomes, of course, of rolling a dice. Okay, now let me clear the screen. If I want to estimate the probability of 6, I have to divide, this is the number of outcomes that are equal to 6, by the total number of outcomes. And it is 0.16. Remember, 1/6 is 0.1666667. And what I am expecting is that the probability is close to 1/6. You may say, it's not really the same, of course, because even Pearson tossed the coin 24,000 times and got the head 12,000 plus 24. So when you make an experiment, you have the effect of casuality, which means uncertainty. But as the number of experiments increases, the uncertainty becomes more and more reduced. It is the same story for climate data. As I told you, we have to understand climate by looking at data, by looking at our experiments. The longer the experiment and the more reliable the assessment that we make. This is why we need a lot of data. So let's go back here, okay? And let's see if it is true that if I increase the number of experiments, I get a more reliable computation. So instead of generating 1 million of dice rollings, let's generate 100 millions, okay? So let's go back to the generation of rollings here, and I add 2 zeros here. By the way, with Excel, you couldn't do a thing like this. It takes some time, you see, R takes some time because, I mean, 100 millions of numbers, it takes some time. Now, let's compute the probability of 6, and let's see if it gets close to 0.1666666. Yeah, sorry, I need to divide by 100 millions. I made a mistake. And you see, it is very close now, much closer. Now let's see with 5. Very close to 0.1666666. Number of 4. Number of 3. Number of 2. Number of 1. Okay, so you see that the power of statistics, and also you see the correctness of our code. Good. Okay, now let's clear the screen and let's go back to the web page, okay? And so we learned how to compute probabilities for an event. And let me also say one more thing. When we passed from tossing a coin to tossing a dice, we made another step further. What is the other step further that we made? I mean, when I toss the coin, the outcome is not a number, it's an event. It's what we call an event. Okay, it's like a flood, like an earthquake, is an event. When we roll a dice, we get in the same way an event, but the event is associated to a number from 1 to 6. This association from an event to a number, it's needed if we want to make analytics, if we want to make an analytical assessment of the outcome from an event. Because, I mean, if I want to compute the average, for instance, I need to associate the event to a number. If I want to know what is the intensity of a flood, what is the probability, no, let me say the intensity, okay? The intensity of a flood, because I can be flooded with 1 meter of water, or I can be flooded by 30 centimeters of water. So this measure, 1 meter, 30 centimeter, basically gives to me an idea of the intensity of the flood. But what I had to do is to convert to a number. Of course, it's not strictly needed. You can say I'm flooded up to my knees, I'm flooded up to my shoulder. But it is, if you want to make an assessment, it's more convenient in engineering, definitely, to associate the outcome from the event to a number. And what is this number? This number is called a random variable, and it's written here somewhere. Just 1 second. Somewhere it's written here, and let me call where is. Let me search for random variable. Random variable. Okay, here it is. In this case, we associated an event, the dice showing one specific phase, to a number. Thus, we implicitly associated a random variable, and you have a Wikipedia link here, random variable Wikipedia, to an outcome from an event. So a random variable is a mathematical formalization of a quantity or an object which depends on random events. Okay. Now, before I move forward, let me make another note, which is extremely important. For the event of rolling a dice, an interesting question may arise. What is the probability of getting an outcome which is lower or equal to a given number? So what is, say, the probability of getting an outcome which is lower or equal to 4? Okay? So a simple reasoning brings us to write the equation 3 that you see on the screen. So the probability of the outcome, let's call it high, less or equal than 4, is equal to the probability of 1, the probability of 2, plus the probability of 3, plus the probability of 4. And therefore, each one is 1/6. The probability is 4 divided by 6, which is 2/3. Can we do it in R? Yes, we can. So let's go back here. And let's try to compute this probability. Now, instead of assigning to the outcome from the rolling a specific value like 6 in this case, I need to say that this must be less or equal than 4. I don't really remember, on the web page there is written how to commute this instruction in less or equal. I'm not sure. I think it is minor equal. Let's see if it works. If it doesn't work, it gives an error, which is fine, because so we can see how errors are communicated into R. I need to add 2 zeros here. No, it is correct. No error, and we got 2/3. Good. Okay. So what we did through this computation, this addition, is to compute the cumulative probability. This is an important definition. So let's distinguish between probability, and probability refers to each single phase of the dice, each single outcome from an event. You can call it also probability mass. If you just say probability, it's fine. If you want to be more rigorous, you can say that the probability of getting, say, 1 is the probability mass of 1. And then let's have clear what is cumulative probability for a random variable. It's the probability of getting a value, an outcome, that is lower or equal to an assigned value. Good. This is an interesting development, I mean, because indeed, in several applications, we are interested in getting the cumulative probability. So think of flooding again. I am interested to know whether the river overtops a levee. So I am interested in knowing what is the cumulative probability of the water level being the same as the height of the levee. Everything is within the height of the levee is not concerning. So if I know that 99% of the time I'm not flooded, this is fine to me, but this is the cumulative probability. Okay, it's not the probability of getting the precise same water level corresponding to the height of the levee. I'm computing the cumulative probability, the probability that the water level is lower or equal to the height of the levee. Good. Equation 3 applies the addition rule for probability. Okay, and there is one thing to say. It works, this addition rule, and keep this in mind, please. It works if the events are mutually exclusive, if the outcomes are mutually exclusive, which is our case. If you get one, you don't get two at the same time. But for some experiments with natural processes, you may get two outcomes at the same time, which means that they are not independent, they are not mutually exclusive. But in this case, they are. The additive or addition rule for probability applies for mutually exclusive events. Okay, good. Keep in mind, and it's written here somewhere, we are now introducing probability, okay, an informal introduction to probability. And keep in mind that what I'm teaching to you, it's an informal introduction. There are some rules that I am introducing, like the addition rule, and there are some features of these rules that I am introducing, like the requirement for the outcomes being mutually exclusive. But I'm not teaching the full theory, okay? And so keep this in mind, okay? It is extremely important, and it is written also here. What follows is not a formal introduction to probability, okay? Okay, good. Let me conclude by saying one thing. So we define probability, probability mass, they are synonym, and cumulative probability. We know how to compute them. I don't want to move forward further. It's already our limiting time. We reached our limiting time. I will move forward further on Monday. I just want to say one thing, which is very important. So we talked about frequentist estimation of probability. We saw how it works, and the Bayesian estimation. So how can we define probability in a word? Does it exist a unique definition for probability? What is probability? This was a long discussion for statisticians. How can we define probability in a way that encompasses both frequentist and Bayesian definition? And Kolmogorov, which was a famous Russian statistician, he was not only a statistician. This is a personality that is extremely interesting. He died not many years ago, I think in the 70s of the past centuries, introduced this formal definition, which is called the axiomatic definition through 3 axioms. And we close with these axioms. Axiom 1. The probability of an event is a real number greater than or equal to 0. Good. We agree on that because we said it is included between 0 and 1. So the definition that we gave, it is consistent with axiom 1. Axiom 2. the probability that at least one of all the possible outcomes of a process, such as tossing a coin, occurs is 1. So if you toss a coin, what is the probability of getting either a head or a tail? It's 1. You will get an outcome, which will be either a head or a tail. So the probability of get any possible outcome is 1. The first two axioms means that the probability is included in the range 0, 1. It is precisely what we said. The third axiom is the additive rule. If two events A and B are mutually exclusive, then the probability of either A or B occurring is the probability of A plus the probability of B. This is the addition rule. So through these simple statements, you define probability, he defined probability. The frequentist approach satisfies, frequency estimation satisfies these three actions. If you use automatically, the frequentist estimation satisfies the actions automatically. If you estimate probability with a Bayesian approach, basing on your perception, you have to make sure that you satisfy the three actions. Good. We can stop here. Let me share the screen and let me stop the recording.